Welcome to Mathematics with Tom. I am Tom, and I'd like to take some time to review integration by trig substitution. I think this is an often forgotten strategy. So I have this integral. The integral I equals the integral of x squared over 1 plus x squared dx. So notice this. Notice that if I try a u substitution, because that's a common place for us to start, it's our first method of strategy that we learned. If I try u equals 1 plus x squared, well, then I get du is 2x dx. And so the problem there is that I lose a power. I need an x squared in the numerator. So this all hinges on this wonderful trig identity, the Pythagorean identity, that sine squared of some angle t plus cosine squared of some angle t is all equal to 1. And there's a few variations of it as well. Notice that we have 1 plus x squared. That doesn't, we don't have that pattern here. So we're gonna find another variation. Let's divide both sides by cosine of t. Then I have the sine squared of t, sine squared of t over cosine squared of t plus cosine squared of t over cosine squared of t equals 1 over cosine squared of t. Let's clean this up. That first fraction is really most commonly written as the tangent squared of t. Cosine divided by itself squared is just 1. And this is equal to the secant squared of t. 1 over cosine squared of t is secant squared of t. Well, there it is. Now this matches the pattern that I have. Something squared plus 1 in the denominator. 1 plus something squared. That's going to be our trig substitution. So what we do is we're going to say let x equal tangent of t. And then if we take the derivative of both sides, so dx dt, and then we multiply the differential, dx equals, well, the derivative of tangent t is the secant squared of t dt. All right, and let's keep that in mind for a little later. Now, let's rewrite our integral. So I now is this integral x squared. Well, x squared is tangent of t squared, so it's tangent squared t. And then we have dx. I'm going to put my dx in the numerator. That's secant squared of t dt. And all of that is over tangent squared t plus 1. Well, now we use our trig identity. And so if what we can say, well, the tangent of t squared plus 1, that's secant squared. So let's rewrite our integral as the tangent squared of t plus the secant squared t d, oh, not plus, goodness gracious, times the secant squared t dt over secant squared t. Well, that worked out so nicely because that just allows us to make this cancellation. We have a secant squared in the numerator and the denominator. So let's clean up what we have. I'm going to rewrite my integral I as the integral of tangent squared of t dt. Now, this one is one that I can never remember, but I think we can solve. Let's go back to our trig identity. Notice that what tangent of t squared, if we look back to this, I'm going to highlight that in bluish, a little blue box. If I look at this box says that tangent squared of t plus 1 is equal to secant squared. But what it also implies is that the tangent squared of t is equal to the secant squared of t minus 1. Secant squared of t minus 1. Okay, so what do we have? Well, then we can rewrite we can rewrite this as the integral of secant squared of t minus 1 dt. Okay, well, let's keep going with that. This is the integral. Let's just break it up because we know the integral of a sum is the same as the sum of the integrals. So this is the secant squared of t dt minus the integral of 1 dt. Okay, well, let's keep going now. Now, the secant squared, that one's not so obvious until you look back to our initial comment, and that was this. The secant squared of t dt, or the secant squared, is equal to the derivative of the tangent. So let's rewrite this as the integral of secant squared. Well, if I take the derivative of if I take the derivative with respect to t of the tangent of t, well, that is secant squared. That's what we did in this step right down here. So we're just using what we've already learned. So, and then we have a minus the integral of 1 dt. So there we go. The integral of a derivative is just the function. So we have tangent of t minus t plus some constant of integration. Now, you might think you're done, but you're not, because remember the original problem was given to us is in x, not t. So here's the next step. The next step says that, recall, we said that x is equal to, somewhere I wrote it over here. Oh, x is equal to the tangent of t. Well, this is just a picture. This is a picture. Here's a picture. It might look something like this. There. Okay, there's my right triangle. So let's just apply a right triangle trig. Here's my angle of t. And it says that the tangent, remember, is the opposite over the adjacent. So you think of this as x over 1. It means my opposite is x. My adjacent is 1. And I can find my hypotenuse. Well, that's going to be the square root of the sides. X squared plus 1 squared, which is just 1. Now I can finish this problem. So the tangent of t is, so my answer is the tangent of t. Well, the tangent of t is just x. I didn't even need that triangle, but it's good to recall. So the tangent of t is going to be x minus, well, what is t? T comes from, let me do this. So we said that x is tangent of t. Well, this implies then if I take the arctangent of both sides, the arctangent of x, if I take the arctangent of t, I just get t. And now I can rewrite. So my integral becomes the tangent of t, but that's x, minus t, but t is the arctangent of x, plus my constant of integration, c. And that is one example of using trig substitution for integration. I hope that helps. Thanks for watching.